637. I'm Charles Bouman. I'm back here today to pick up where... Oops. Oh, my mic. Thank you. Let me say that one more time. This is E637. I'm Charles Bouman. I'm back here today to pick up where Jordan left off and talk about minimum mean-square error prediction with training. On Friday, we have the exam. So the exam will have 3 problems on it. It's pretty much similar to the last exam, only the problems are different. Well, it didn't have to be different. I mean, I could have just given you the same one again. It would have been less work. But let's see. What else should I? Coverage. I think I emailed about coverage out. It covers up to and including material on decimation and interpolation, right? And let's see. I think that's pretty much it. Probably immediately following this lecture, there'll be an armed guard who will come from EPE and obtain the exam from me because it's way late. But other than that, any questions? Okay, so we'll pick up where we left off. So you learned about doing, actually you've already done the lab for minimum mean-square error filtering, right? Yeah. So let's see. There's actually some very interesting, so there's some very interesting things to learn from this lab. I mean, first, the minimum mean-square error filtering is in itself valuable, but there's some larger lessons to learn. Okay, one of the lessons is in the general strategy of how we're doing this, which is that you have an image here. So this is distorted. And this is undistorted. And you might say, well, if I have the undistorted image, why am I bothering to do restoration? That's a good question, as a matter of fact. Well, usually what happens is that you can obtain some undistorted versions of the image, but it's very costly. But you can obtain them at high cost. And for some small number of cases. So and then you take the idea here in your lab is you take a window of pixels, and then you predict the pixel here. So you use this entire set of pixels to predict that one pixel. And then what happens is that now what you have, so this is X. So this is X, and this is Y. I think this is the way we're doing it. And so then what happens is that you have another set. You have a Y here. So this is a new Y. And from here, you take pixels, and you produce estimates of the pixel here, right? But this thing is now going to be X hat. This is your predicted value, okay? So so if you had the answer, why did you even bother to do the problem? Well, the reason you did the problem is because very often you don't have the answer. So this is called the training case. And this is called the testing. So, ideally you have lots and lots of training data, but training data is expensive. And often training data, this is often called ground truth. The reason it's called ground truth is from the remote sensing application. In remote sensing, you might have a satellite in space or an airplane looking down. You're making measurements, and then you want to know what the correct answer really is. So you're trying to predict what's on the ground or make some estimates of what's happening. So you go on the ground. Usually you find a graduate student to do that because they're less expensive. Okay, so then you have them walk around on the ground and check, and they go, oh yeah, okay, that pixel's red. So that becomes ground truth. Now you could actually eliminate all need for satellites. What you could just have is like millions and millions and millions of graduate students walking around all over the place, all over the surface of the Earth, and checking out to see what it is. But that would be very expensive, and the graduate students would get bored too. Okay, so, and it's always dangerous to have bored graduate students. So instead, you pay a lot of money to obtain ground truth for a small amount of data, and then from that you try to generalize it to predict what's going to happen in other cases. Okay, so now it raises some interesting questions. One of the questions is, how much training data do you need? How much ground truth do you need? Since it's expensive, you want as little as possible. Okay, and how do you assess performance? Okay, well, it turns out that if you have, so let's say I train in your example, you trained on a certain number of pixels, and say the number of pixels here is n. Okay. And what happens is you find that if you so this is kind of like a factoid plot. So if you look at the performance as a function of n, okay, it's very interesting what happens. Okay, so if you look at the error on the, so you have over here, if you have 1 pixel and you try to predict the 1 pixel from this window here in the training data, how much error should you get? Well, you're just trying to predict that 1 pixel. You're training on it to do the best prediction possible. How much prediction error should you get if you try to predict only 1 pixel?
I'm not sure what you're asking.
Excuse me?
I'm not really sure what you're asking.
Yeah, it's a little unclear. I'll ask it again. So if you have this training image. You have 1 pixel, and you only want to predict that 1 pixel, and you're allowed to pick these parameters however you want to minimize the prediction error. How much prediction error will you have when you predict that 1 pixel?
None.
None. 0, right? It's like if you were going to build an image coder, and the only thing the image coder ever had to transmit was the Mona Lisa. Then the number of bits you'd need to transmit would be very small, maybe 1, because you just have to tell the person, I'm transmitting it now, okay? And when they receive that 1 bit, what they would do is they would just decode the Mona Lisa that had pre-coded in advance, okay? So it would be like the Mona Lisa coder, okay? The problem with that is it's not terribly useful, okay? But it's very effective, okay? Now, so what happens here is that, so that you have this sort of counterintuitive result that if this is the error, say mean square error, okay, or some other performance distortion metric, okay, that when n is 1 or when n is small, actually the error is 0. In fact, you could, if you have, 10 parameters here. So let's say it's 9 parameters because it's a 3x3 window. If you have 9 parameters, then you can predict up to 9 pixels perfectly, right? When you get to 10 pixels, now the error will start increasing. So if n is very small, the error will be very small. And then as n increases, the error will increase, okay? And then you'll get something like this. Because if you have, as you get more and more pixels, eventually you'll sort of achieve an upper bound. You'll asymptotically move towards an upper bound. Okay. Now, if you then take the results of these parameters and you use those parameters to actually apply to a new example that you didn't train on, so this is the testing data, and you look at how much error you got on the testing data. If you only had 1 training pixel here, what would you expect the error to be on the testing data? it would be very high, right? So it'll be way up here. It'll be way up here. And as you have more and more data, you would expect it to go down. So you get this kind of behavior, where hopefully these will converge together as n goes infinity. And so this is the performance on the testing set. And this is on the training. So what you learn from this is that if you use the training data to assess, you need to use the training data to estimate the parameters of your model, of your prediction model. But if you use the training data to assess the performance, you're going to have a very optimistic result because you cheated. You know the answer to your problem. So you get an unrealistically positive assessment of the performance. This is actually handy because if you need to mislead somebody, then you could use this to confuse matters by testing on the training data. Okay. Now the problem with that is that it's not an accurate assessment, so I would strongly discourage you doing it. Okay, but so the moral of this story is never test on training data. Training data. If you do, you'll get an overly optimistic estimate of performance. And generally, the relevant quantity tends to be the ratio of the amount of training data you have, where n is the actual number of scalar values in your training data, divided by the number of parameters. If the amount of data equals the number, is less than the number of parameters, then it's often the case that you have fewer equations than you have unknowns. You can adjust the unknowns to get a perfect fit. But as the ratio of this thing becomes large, then your estimate, the performance on the testing and the training data should be similar. Now, if you want to be out here because that's when you're getting the best performance. So if you have too many parameters in your model and not enough data, you'll be over here where the training data will perform very well, but the testing data won't. So that's one way of determining if you have enough training data. So this is a very fundamental problem because it comes up in many applications, not just this image restoration problem. Any problem where there's parameters that have to be estimated for a model to fit into data, you're going to have this problem that you need to have much more data. You'd like to have much more data than you do parameters. And one way you can assess whether you're in that realm is if your performance in the training set and the testing set are similar. Now, so one of the big mistakes people make when they publish research is they test on the training data. And that can be very misleading. Sometimes it's obvious when you're testing on the training data, but sometimes it's not so obvious because if you have a very complex process, sometimes the training information can leak into your performance assessment in a way that's not so obvious. Here's an example. So if you have a lot of typically what you'll do, by the way, even to get this performance curve, I need to take my ground truth and partition it up into two sets. So let's say I have 100 images. So some 100 images of ground truth. Some of those ground truth images I'll use to train. If I use all the ground truth images to train, then there won't be any ground truth left to test with. So usually what you'll do is you'll partition it up. It might be 50-50, it might be 1/3, 2/3. So you might take 2/3 of the data and train on it, and 1/3 of the data and test on it. Now, as you use more data for training, you'll get a better result. But the problem is you'll be uncertain about how good that result is. So there's a trade-off there. But one way in which you can, there's lots of ways in which you can essentially use training data to test in inadvertent ways. So what you could do is this: you could train your algorithm. You could train like a few different methods, okay, on this training data, like say 3 different methods, okay, and then you could test the 3 methods on the testing data, and you could only show the results from the one that worked the best. Okay, that would be. You'd say, well, I only trained on the training data, and I only tested on the training data. I only tested on the testing data. But you've cheated because you've looked at the result, and you've thrown away the ones you didn't like, right? So effectively, that was a form of training on the testing data. So this is very important, and if I'm ever on your thesis committee, and you show any kind of results of some sort of algorithm you developed, I'll inevitably ask this question. So you should be prepared in advance before your oral exam, right? And the answer should be, I'll ask, have you trained on the testing data? And the answer should be, no, I haven't. Okay. It's very important, and it's a little insidious. And there's also a very strong desire, unconscious desire to cheat, okay? Because you want to make your advisor happy. It's understandable, okay? But you have to be very cautious about that. Yeah, you have a question?
I have a question. For this training, why don't we use, instead of using all the training data, kind of weight the data, some part of the image? For instance, you mentioned the example of airplane on the sky. What if in the image we find that airplane and the significant part of the image and weight more?
There's that one word I'm missing in your question. What part of the image I couldn't quite make out the word you said.
Weighted?
Weight the
significant part or the important part.
Yeah, okay. And how do you know which part is important or significant?
Well, we can weight it based on what we want. For instance.
Mm-hmm. Yes.
Yeah. For instance, you mentioned the example of airplane.
Of what?
Airplane.
Oh, airplane. Okay, that's the word I was missing. Okay. Yeah. So if you had an you say, if you're flying, in a remote sensing application, right? Yeah.
Right.
Mm-hmm.
So in this way, instead of having lots of data, training data,
right,
I can have some weighted training data.
Right. So there's a few issues there that you're raising, I think. One is that, you can weight. Some values may be more important than others. So you can say, and that tends to be application specific. Another thing is that, now, in general, more data is better. So if you have more training data, you'd like to be able to use it, but in practice, you may be limited, say, for instance, computationally. Usually it's the opposite case, where you don't have enough training data. Sometimes what will happen is you have a lot of training data, but it's highly correlated. So for instance, if you have like a few images, each image is maybe millions of pixels. So you have a lot of training data, but it's only from a few images. And there's sort of an assumption that the distribution of the pixels within an image are sort of related in some way. So when you sample from multiple, so you want to have a lot of different images. That would be an example of how you can cheat. That's a good example of how you can cheat inadvertently. So what you could do is this. Let's say you have three images, and the 3 images are sort of all similar, or maybe from the same scene, okay? And what you do is you randomly select subsample pixels from the 3 images, and you train on these images, but your test pixels are subsampled from the same images. So now what's going to happen, that's going to be an unfairly optimistic result, because you're essentially like training you're testing on the training data. Because if you got a 4th image, you might find that the 4th image was qualitatively different than the first 3, mathematically, one way of explaining that is saying that all the pixels within a single image are all have the same distribution, right? But that the new images, its pixels have a different distribution. So you need to have a lot of images so that you see the distribution of all the different ways pixels can behave. So in that case, you get a more accurate assessment of what was going on. If you had, say, 10 images, you trained on 8 of them, and you tested on the other 2. And the other 2 were picked randomly from the set of 10. Okay, so there's a lot of different ways. There's kind of a subtle issue. There's also this thing called cross-validation, which is a clever idea. And once you know it, you'll never forget it because it makes a lot of sense, right? That what you could, and it's specifically to get around this problem. So let's say you have, I don't know, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 points. What you'll do is this. You can say, well, 1, 2, 3, 4, 5. So you'll take, I should have made it 9. 10, 11, 12. Okay. Okay, so take 4. So we'll take 1, 2, 3, 4. So I take this group of 4 points, and I take this group of 8 points. Right? So I train on these 8, and then I test on those. But now the problem is that's just one example, so it doesn't give me a very good estimate of the variance. So what I then do is I now do another partitioning. So now I train on these and I test on those. So this is test, train. This is train, and this is test. Okay? And now I can do a third one where I can take 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So now I can take those and I can take these. So now I can do 3, and this is train, and this is test. So I can do three different partitionings. Each one I can train on here and test on that, estimate what the variance of my estimator is, and then average the variances across the 3, and I'll get a better estimate of how accurate the method is. Okay, this is called a round-robin partitioning. It's the general methodology is called cross-validation because there's a lot more sophisticated ways it can be used. And in the most extreme case, I could just train on 11 points and test on the 12th, and then I could do 12 of these sets round robin, but it gets computationally expensive. Okay, but this is a very fundamental problem, very, very, very fundamental, because as boring as it may sound, parameter estimation is one of the most fundamental problems in information processing. Basically, it is the canonical problem because so estimation sounds like very boring, right? But the problem is I can always come up with very complex models of the world. The problem is I don't have any way of fitting parameters to those models. If I have too many parameters to the model, and the model's very expressive, but there's no way I can never collect enough data to be able to fit the data to the model. If I restrict the number of parameters, then the model's not very expressive. I may not be able to get a good fit to the real data, but at least I can get enough data to train the model, because I need to have more data than parameters generally. So this is another way of looking at the fundamental trade-off between bias and variance. When you have high variance, it means that your estimate was based on very little information, so your variance is high, but the bias is low because you used a lot of parameters in your model, so you had low bias but high variance. If you use a small number of parameters, you tend to have high bias but low variance. So there's a trade-off between those two. Okay? Any questions about this? It's a very, very important topic. and we're just touching on it here. Okay, one thing to go through really quickly is that minimum mean square error linear filters. I spent a lot of time explaining that minimum mean square error was not a good measure of quality. So why are we using it here? Well, it definitely is not in general a good measure of quality. And even for this case, there could be better ones. But it's not so terribly bad, because it turns out that if I had made this minimum weighted mean square error using any weighting, any quadratic weighting, I would have gotten the same answer. So the mathematics behind it is like this. If I use, if I modeled the human visual system as being a linear filter, and then I computed mean square error after linear filter. So we talked a lot about distortion metrics, and in our distortion metrics, there's usually some sort of spatial filter that approximates the modulation transfer function in a human visual system. So that would be H here. So that's a matrix. It could be like a linear space invariant filter, but it doesn't have to be space invariant. It just has to be linear. Then if my objective is to minimize that filtered difference, then it's like I'm minimizing the expected quadratic norm. It turns out that if you minimize the expected quadratic norm, it's the same thing as minimizing the expected norm, because in both cases the minimum mean square error estimator of x is the conditional expectation of x given y, right? So that's a justification for using mean square error. It works okay for these sorts of problems because it's equivalent to a large class of distortion metrics, some of which represent a human visual system not terribly bad. Okay, I wouldn't say that they're great models. They're not. They're at best mediocre, but they're not as bad as mean square error. Okay, and this is just the proof that minimizing this quadratic norm with some positive definite matrix B is the same thing as minimizing just the plain old conditional. It's minimized by the conditional expectation, which is also the minimizer for the normal mean square error. So basically, for the purposes of minimum error under any quadratic norm, the result is the same. It's always the conditional expectation. Okay, which is a little bit of a surprising result, I think. Okay, are there any questions then? Because if not, I'm going to go on to nonlinear filters. So, yeah, we're going to just touch on some nonlinear filtering techniques. Yeah?
Excuse me, Professor. I think the minimum mean square linear filter hasn't been covered yet. The least square linear filter hasn't been covered. I mean...
Oh, hold on for a second. Oh, you didn't do the least squares case? Oh, I'm sorry. I thought that Jordan covered that. Okay. I see. Right. I thought there was a lot that he had covered. Okay. So, well, that's okay. Then I covered the training and testing. Okay. So you did the minimum mean square error linear filter, but you didn't do the least squares case. Okay. So, okay. Okay. So. Hold on, where is the result here? I thought you did... Okay, you did this, right? So you did this, right? You did. You set up the problem, right? So Jordan did the minimum mean square error case without doing the least squares case?
No. I covered the least squares case.
Oh, you did cover the least squares case.
Yeah,
So let me just make clear what the difference is between the least squares and the minimum mean square error case, right? So in the they're subtly different. They're closely related. One requires training and the other one doesn't. If I want to compute the conditional expectation, if I want to compute the minimum mean square error estimate of x hat, given y, so this has to be a function of y, right? It's the conditional expectation of x given y, right? So, and in that case, I think you can show that. I'm afraid to try to drive the equations right now because I'll end up making a mistake. Okay, so if I want to minimize, so I know the form of this. This is the conditional expectation is a linear function of y if these are all jointly Gaussian. So if I take if I have x minus theta times y, right? Theta is a row vector, and y is a column vector, and x is a scalar. So here, x is, say, it looks like a scalar there. This is a row vector, and this is a column vector, right? And then I take this thing here and I square it, right? So I take this thing here and I square it, and I want to find, I want to minimize the expected value of this thing. I'm running over theta, and that's theta hat, right? So, so if I do that, then the expected value of x minus theta y squared, that's equal to the expected value of x minus theta y I have to be a little careful. I'm doing this without a rope, because if I get the transposes in the wrong place, I think I don't want to use, okay, I think I want to do it like this. Maybe I'm wrong. I want to do it like that, okay? So that's equal to this. I could have put the transpose here or here, because these are scalars, so either way it works out the same. Okay, so this is then equal to the expected value of x squared, that's just a scalar, minus 2 times theta times the expected value of y times x, okay, that's a column vector, plus theta times the expected value of y transpose times theta transpose, right? So now this thing here is the covariance of y, right? So I have that this function here is the expected value of x squared minus 2 times theta, the expected value of xy. I can do this either way because that's a scalar, so I can multiply on either side. Minus theta transpose, the expected value of y transpose theta, right? This thing here I'm defining as b, right? And that thing here I'm defining as r sub y, right? So now I want to minimize this. So if I want to minimize it, I compute the derivative. So this is, and this I'm going to just call, I don't know, c. So this whole thing is equal to c minus 2 theta b minus theta transpose ry theta, right? Now I want to find the minimum of this, because this is the expected, the mean square error. So I take the gradient, so I compute the gradient of this function f of theta, and it's equal to, well, the derivative of c is 0. So this is minus 2b, and then this is minus 2ry theta. Oh, hold on. That transpose is on the wrong side. Transpose, right? And that whole thing has to equal 0, because the gradient has to be 0 at the minimum. So the 2's cancel out. I got something messed up here. This is supposed to be a plus. This is the problem with trying to do it in real time. Okay, this becomes a plus, and that's a minus, right? So this becomes ry theta transpose equals b. So theta hat, the minimum of this is achieved by ry inverse b, okay? Now the problem is, so this is fine. This is the minimum mean square error predictor. The problem with this is, so this is the minimum mean squared error predictor. It's not minimum mean square error predictor of theta, okay? It's the value of theta that achieves the minimum mean square error prediction of x, okay? So this is minimum mean square error, but the problem is that, is this a random variable or a number?
Number.
So R here is formed by an expectation. So is it a random variable or a number?
Number.
This is a number. That's a number. Everything here is a number, right? So there's nothing here that's a random variable. So actually, I'm putting that as a hat, but really that's kind of a bad notation, because I should maybe mark this as theta star, because it's not random. Usually hatted quantities are random because they're estimates. So this is not random, and that's fine, and it's optimal. But the problem is you need to know what the covariance R is and this cross correlation B. Now to do that, you might try to estimate R and B, and then try to plug your estimates of R and B into this formula. But then you don't know how much error you're going to have in your estimate of theta, and what's going to be the resulting impact of that error in theta on your estimate of x. In the end, your estimate of x hat, is going to be equal to theta star times y, right? Now, and you might say, well, it doesn't really matter that much. Well, it can matter a lot, because some of these errors can start to become quite large and dominate your problem. So, the fundamental problem here is that you can talk about the minimum mean square error estimate and computing the conditional expectation, but it's difficult to do unless you have omnipotent knowledge of exactly what the models are for your data, and usually don't. So instead, there's an alternative viewpoint called the least squares problem. So this is minimum mean square error, but there's an alternative view, which I think Jordan explained, right? Did he go through it? Which is the least squares. In the least squares problem, what you do is you say, okay, instead of solving the minimum mean square error problem, instead what I'm going to do is I'm going to take the actual observed error. So I'm going to sum over, well, okay, that's where you have this expression here. Okay, so you take xs minus zs times theta. So here, zs and xs are actually random variables and random vectors, because they're actually sampled from the data. So instead of trying to calculate the exact minimum mean square error estimator, you can't calculate it because you don't have omnipotent knowledge of what the distribution of the data is. Instead, what you do is, for a particular empirical data, you actually find the values of theta that minimize squared error over that data. This is called least squares. So the result of this, theta star from this, see, there's no expectation here. In this case, the theta star, these are random variables. So the solution to this is what? A random variable or a number?
variable.
It's a random variable. So least squares produces an estimate of the unknown parameters, whereas minimum mean square error isn't about estimates. It's about actually calculating the parameter that results in the minimum mean square error. It's just a number. Okay. So in practice, least squares is what you usually have to actually do, because you don't have all the information you'd like to have, and that's where you get into this problem of estimation, and that's where the issue of ground truth comes in. I mean, if you see this in this curve right here, if you had this error here, this would be the minimum mean square error. That's the best you can do if you have omnipotent knowledge of the distributions. All right. But usually you don't have this, so instead you have to estimate them, and there's going to be some degradation in performance. So this is how much you lost because you didn't have enough data to estimate the parameters accurately. Okay, is that clear? Is the difference between least squares and minimum mean square error clear? Any other questions? Okay, it's actually very, very, very important things. But by the way, you know, I mean, learning specific details of how to do particular calculations, while extremely important, particularly from the point of view of doing well in the exams, well, is in some sense not the most important takeaway. Okay, for this class, it's very important to have the understanding of the broad idea of what it is that the challenges are and what has to be balanced, because that's the thing that you'll see that will recur time and time again when you're actually either doing research or implementing some system for a practical application. Okay, so this isn't just kind of make-believe stuff. This is real problems that face people in real applications all the time. Okay, now, nonlinear filters. So, okay, we've spent the nice thing. We spent a lot of time talking about linear filters, and we had the minimum mean square error linear predictor that we trained. Okay, and the nice thing about linear filters is that they're easy to design. They, there's a whole theory that's all self-contained and beautiful that happens to be true, right? I mean, it's all wonderful, but it's all predicated on the linear filters are optimal if the noise is all the distributions are jointly Gaussian. If the distributions are not jointly Gaussian, then the linear filters are no longer optimal. So, is an image a Gaussian random process? No. Why? It's not a random process, okay? But in addition, is it well modeled by a Gaussian random process? Sometimes. Is it often well modeled by a Gaussian random process? Usually not. Why? What would be an example about something in it that's not particularly Gaussian?
You had a pattern that reoccurred?
Well, yeah, I mean, you could, that would make it, yeah, that's true. But for instance, if you take an image, right? So actually, this is a really simple example you can do, which I should include in one of the labs, actually. If you just take an image, right, and you take pixels next to each other, and you take their difference, and you histogram it. Mm-hmm. For a typical natural image, do you think it'll be Gaussian? Gaussian would mean it would be like this. So you take nearby pixels, you take yn equals, or I'll make it dn equals xn minus xn minus 1. And you take this and you histogram it. Everybody knows how to histogram, right? Because we had a histogram equalization piece to one of the labs, right? So it will look like a Gaussian distribution and a typical image. Well, it could look like anything, right? Because it's an image, I could just make the data up to come out however you want, okay? But if you take a typical image, try it. Just take some image. Take a picture, okay? And take this, okay? The distribution will look very heavy-tailed. Typically, it looks pretty Laplacian, actually. Amazingly accurately modeled by Laplacian or some relatively small variation on it. The tails are very heavy. Now, why do you have real heavy tails? edges, right? Because at edges, these differences can become enormous. So images are not well modeled as Gaussian random processes. And the places that are really behave not Gaussian are edges, right? Edges are not very Gaussian. So linear filters tend to blur edges and other image detail because edges are not very Gaussian. Yeah?
How about the stick stationary?
Excuse me?
Stick stationary random processes.
Strictly stationary? Well, okay, so stationarity doesn't have anything to do with, isn't directly related to whether something is Gaussian. So let me give a 1D example. We learned about AR processes, right? So a simple AR process would be like this. You could take this guy. This is like, this is plus. So this might be, 0.9 times z to the minus 1, okay? So the impulse response to this thing is going to be h of n equals u of n times 0.9 to the n, right? So if I put Gaussian, so this is y of n, right, and this is x of n. If I put a Gaussian random process in, I get a Gaussian random process out, right? Because this is a linear operation. So any linear operation applied to a Gaussian random process produces a Gaussian random process. So this is, and if this is stationary, that has to be stationary, right? Because this is time invariant. So if I put, a typical case here would be white noise. So you put IID, and you could say N0, 1, okay? In that case, the output signal here will be a Gaussian, right? But another possibility is I could put non-Gaussian noise. So I could put some very heavy-tailed noise in there. One possibility is that I do something with high probability x of n is 0. And then with low probability, it's a Gaussian random variable with mean 0 and variance 1. So in that case, so this could be non-Gaussian. And it could be impulsive. Impulsive means that it's 0 a lot and then it's very large, okay? So in that case, if you look at the signal, it'll look like it'll be going along, and then all of a sudden it'll jump up, and it'll decay like this, and then it'll jump down and decay like this, and then it might go like this. That would be what the random process looks like. That's a stationary random process. Is it reversible? Did we learn what reversible is? I don't think so. But if applying any kind of reasonable definition of what you might think the word reversible is that reversible? No, because it looks different going forward than backwards, okay? Okay. Now you have to develop the theory behind that concept. I'll assign that as a homework problem. But but it's stationary, okay? Is it Gaussian? No. So are all stationary random processes Gaussian? No. Okay. If I take differences between adjacent pixels, actually, if I subtract adjacent pixels, if I put this through a filter, which is like this, if I multiply by 0.9 times z to the minus 1, and then I subtract plus minus, that's actually the inverse filter. So the output here would then be x of n. So I know exactly what the distribution of these would be. There would be the distribution going in the first place, which if I made it a very heavy-tailed distribution, it would be heavy-tailed again. So this is almost the same. Subtracting nearby pixels is almost the same thing as this, right? Because I take each pixel, I subtract each pixel oops, I'm out of time, okay? But my point here is that this is sort of the intuitive justification why when you take edges they look Laplacian, because images are not well modeled as Gaussian. All right? Good. Thanks.